Yeah, okay. With having looked at this transformer model, we're going to look at how we can actually apply it to a real transformer. So what we need is a way to find out the values of these model components, the R1, the X1, R2 and X2, and the RC and XM values for a real transformer, if we're going to be able to do this on-load, off-load analysis. Now we can't find the individual values of X1, X2, R1 and R2, but we can find the value of them all combined together that we just now used in that last example, and we can find a value for the parallel components for the open circuit situation, and we do that using two tests. So we can find the values of the loss impedances in a real transformer model through a practical experiment that involves an open circuit test where we measure the input power, the primary and secondary voltages and the primary current. And then we do a short circuit test, so short circuit the secondary, input a much lower voltage, taking care not to exceed the VA of the transformer, and we measure the power input, the primary terminal voltage and the primary current in a short circuit situation. Okay, and then the following example will demonstrate how we use those values to determine the values of the components we need for our model. So when we do the open circuit test, we get the wattmeter provides us with the power loss in the core. So it provides us with the watts lost due to heating in the core. The apparent power supplied by the source we can get from measuring the primary current and the primary voltage there and there. And then because we've calculated the power here and the SM there, we can use those two values to find the reactive power in the core using Pythagoras theorem. We can then find the value of the resistance, RC, representing the core loss, from the primary voltage squared over the measured power. So that gives us RC. And we can find the magnetizing reactance from the voltage squared over the calculated Q for magnetizing. And then the fact that we've measured also the secondary voltage, we can use that to find the transformer ratio I. So from that one test, we've found out the value of these two components, RC and XM, and we've found out the value of I is the transformer ratio, turns ratio. So this is different to using in that previous example we used the nominal primary and secondary voltages to determine what the turns ratio should be. This is finding out practically, to as near as we can, what the turns ratio actually is. Right? So we use the two measured voltages to do that. That gives us a model like this one down here, where we can include the values of RC, XM, primary secondary voltages and turns ratio A. So we could then model the offload situation of that transformer. You all happy with that? Then When we do a short circuit test, so we connect together the two terminals of the secondary so they're short circuited, and then we carefully increase the voltage, making sure that we don't exceed the VA of the transformer. So we essentially work out a voltage or turn it up slowly until we making sure we don't exceed the rated current on the primary side, secondary side as well. So it might pay as well just to put an ammeter in here to keep an eye on the secondary current as well. We don't want to burn that out. Okay. And then we get the transformer impedance. That's the R1 and the R2 and the X2 transferred to the primary. We can get from the short circuit voltage. So we're measuring the short circuit input voltage of the transformer divided by the, so we're doing that divided by that gives us the effective impedance of that transformer, and the transformer resistance referred to the primary is this power divided by that current squared. Okay, and the leakage reactance can then come from Pythagoras' theorem with those two values. Alright, so that gives us this one from there, and this from there. By doing a short circuit test. And that's the circuit we've effectively got there. We used those values to find those two values. We can then disconnect, we can then put a load. So if we effectively take, I can't do it on here, if we take that out, we've got a value for EG, we've got a value there for those two components. There's our model of our transformer that we can now put a load on and do an analysis. Yeah? Just by doing an open circuit and short circuit tests, we could do open and short circuit analysis on a real transformer. And if we wanted to, we can add the core loss components in there as well. So, example 3, using open and closed circuit tests. Have a go at that. I'm going to let you have a start at it yourselves. Okay, work together and see if you can use open circuit and closed circuit results given there to find values for the transformer components and find the active power delivered to a load of per resistance 50 ohms and the power supplied by the source and the efficiency of the transformer under these conditions. Okay? What we'll do next week is we'll do that with that real transformer. So we'll get those results and then we'll use it to analyse the way that transformer will work under load. So you've had a go. What we'll do let's go through my workings of this example. We're going to start off by looking at the open circuit situation. So I'll deal with it separately. Open circuit. Okay. So where did you start with that? Let's find out how far you got and then where you got stuck. Yeah. So if you follow from what the open circuit tests give you, you simply calculate these values or state them. So PM was, from the test given, 5 kilowatts. Then it calculated SM from EP times IP. We had 69 times 10 to the 3, 69 kilovolts, multiplied by 0.15 amps. That equals 10,350 VA. Right. What you've got to be careful of is none of these values relate to the real situation of that transformer with a 50 ohm load connected across it and 69,000 volts stuck on the primary. These values don't relate to that. All these values are as a way to find those component values inside the transformer. From that we get QM. That's the root of S squared minus PM squared. So we were given the P, that would come from the wattmeter test. We used that to calculate S, and in the end we used the voltage and current to calculate S. So that is the root of 10,350 squared minus 5,000 squared equals 9062 var. Did you all get that far? Yeah? Are these figures what you got, Matt? Yeah, you've got to be careful with that. If you square numbers with the power 10 notation, you've got to put the number of power 10 notation in brackets.
On my road I did, but where I only calculated nothing.
All right, so we've cleared that one up. Okay, and then we can get one of the values we're looking for. RC comes from EP, a measured value, squared divided by the power, 69,000 squared over 5,000 came out at 95220 ohms, and I just shortened that to 952 kilos. We'll get that far. Yep. And XM EP squared over QM 69,000 squared over the 9062, and I made that 525380 ohms. All agree with that one? Is that what you got? Yeah? And then lastly, the transformer ratio, EP over ES 69,000 over 4160, 16.6. Yeah. So that's the open circuit situation for that transformer, determining values for RC, XM and the transformer ratio. Alright, so the open circuit part, not too bad. And the only bit from there we actually need in the second part of the analysis for on load, we need to make a note I of 16.6. And what we're looking for here is determining the values for this circuit. Such that when we connect a load across here where Z is equal to 50 ohms, this is Z dash, we can use that to model what happens when this actual load is connected to it. So we're going to use the short circuit results to try and find values for RP and XP, and therefore find that model. We can then reflect things back to secondary side and find out how much power is being dissipated by this load, and therefore we can find out the efficiency of this transformer. And from the example given, we can calculate ZP from E short circuit over I short circuit. That's the total impedance connected to this transformer, at least the magnitude of it, from 69,000 over, no, hang on, not 69,000, 26,000 was the applied short circuit voltage over 4 amps. I made that 650 ohms. Everyone get that far? No? So all you had to do was follow the example short circuit test there. RP can come from the power measured in the short circuit, which is in the results, divided by the short circuit current squared. That's derived from P equals I squared R. And the short circuit power (2,400 watts) divided by 4 squared. I made that 150 ohms. You lost where, Luke?
I don't. Oh, right, okay, it's a typo. ESC on this handout for it to be.
Yeah.
Yeah, I'm not sure.
Alright. The primary voltage applied, which is a short circuit voltage, 2,600 volts. PSC, 2,400 watts. We'd measure that with a watt meter. And ISC, 4 amps. Yep. An unfortunate crossover of notation, but all that mean is, all the SC mean is what voltage did you apply to the short circuit test. And I got that right, 150 ohms.
Yeah.
Yep. Now we know, if we, let me just focus in on where this information comes from. What we've now got is a total impedance and we got R. We got that and we got that. Yeah, remember this time there's no, at this point, because we're talking about the circuit under these conditions, take that away, short circuit, ZL dash at the moment is nothing, because nothing times A squared is nothing. Got me? So we're using the total impedance of that, and we've just found RP as well. So we got those two sides of the triangle. Can we now find that side of the triangle? Yes, we can, can't we? How? Yeah, so XP I made that 632 ohms. All agree? Yep. Right, what I'm going to do now is go on a new page and draw out what we got here. There's our generator. That's delivering 69 kV. And we got an RP in there of 150 ohms. An XP in there of 632 ohms. That we would label on our notation E2 dash. And we've got a ZL dash there. That's the circuit we've now got to analyse. Okay? ZL equals 50 ohms. Therefore, ZL dash is equal to A squared times ZL, 16.6 squared times 50 equals, and I made that 13778 ohms. And that's purely resistive because that's what the question said. So total impedance is that. Do you agree? Add them all up. 13778 plus 150 plus 632J ohms. These two here combine together, making 13928 plus 632J ohms in total. And I converted that to polar form because that's what I need it in. That come out of 13942 angle ohms, sorry, ohms angle 2.6 degrees. We'd expect that narrow angle because this big ZL dash is making the resistive part massive compared to the reactive part there. Okay, so you're expecting a narrow angle. Now we know the total impedance of all three components added together. Surely we can find this current IP, can we not? Yep. Off we go then, find the current. All agree with that? Primary current is the primary voltage of the total impedance. Comes out at 4.95 amps, angle minus 2.6 degrees. Everyone agree? Yep. Now, overall, what we want to know is how much power is this generator supplying to the total circuit. Because overall we're trying to find the efficiency, and we need the power in and the power out to do that. Okay, but now we know the voltage, 69,000 volts. Now we know the complex current, we can find S. If we can find S, we know S is made up of P and Q. So if we can find S in complex form, we can turn it into rectangular form and pick out P and Q, can't we? So we can go S generator, S supplied by the generator is equal to IP times EP. That's 4.95 angle minus 2.6 times 69,000 angle 0. All agree with that? And I got 341,550 VA angle minus 2.6 degrees. Convert to polar, to rectangular, sorry. Equals 341,198 watts plus, sorry, minus 'What I'm saying there is, this bit Now we've turned that complex S into rectangular form. That bit is the power supplied by the generator in watts. All happy with that? So let's put it in here. 341,198 watts. You're going to find, P secondary power dissipated in ZL. How can we do that? You can't reflect that power because that power there is not what's here. You're going to get into trouble if you start reflecting powers. But what you can do is find this voltage and reflect it over the other side. Find the primary current reflected over the other side. Multiply them two together to get S on the secondary side, and then extract the secondary power from that. Okay? What we'll do is I'm going to leave you to try and finish that off now. I'm going to save that as it is, and then finish that off in the remaining time plus between now and next week, and we'll start next week by finishing that off on the board, and then we'll go to our analysis of our practical transformer after that, which will essentially be doing these calculations but on some real values. So copying this example and finding out what that transformer is going to do on load. Okay? So just to summarise, what you need to do now is find E2 dash and reflect that to the secondary. Reflect IP to the secondary. Multiply them together to get S in the secondary. Yep. And then extract the power out of that, and then P out of a P in will give you the efficiency of the transformer.